For thousands of years, granite monuments have sat across Egypt as if the hardest stone on earth were simply another building material. At Aswan, ancient workers left behind enormous unfinished blocks, deep trenches, and thousands of battered dolerite pounders. Yet the question becomes far more difficult when we look at the saw cuts, drilled holes, and polished surfaces left on finished granite. The evidence suggests the Egyptians had several ways to attack this stone, and the real story may be much more practical, complex, and surprising than the familiar image of copper tools alone. Granite does not behave like limestone. That difference is the first thing to understand. Much of ancient Egypt's monumental architecture was built from limestone, a material that can be cut and shaped relatively easily with stone and metal tools. Granite is different. It is an extremely hard igneous rock made from several minerals, including quartz and feldspar. Some Egyptian granite working surfaces are among the most demanding examples of ancient stone craftsmanship. And yet the Egyptians used granite repeatedly. They used it for sarcophagi, columns, doorways, lintels, statues, obelisks, flooring, and architectural details. At Giza, granite appears in some of the most carefully constructed parts of the pyramid complex. Farther south, Aswan became one of the great sources of the stone. The famous unfinished obelisk gives us something even more valuable than a finished monument. It gives us the worksite. The giant obelisk was abandoned while still attached to the bedrock. Around it are trenches and enormous areas of granite that were deliberately removed. Nearby, archaeologists have also found large numbers of dolerite pounders, hard stone tools used to attack granite. This is important because it destroys one simplistic idea immediately. The ancient Egyptians did not need a mysterious machine simply to break granite out of a quarry. There is physical evidence for how they did that. Dolerite pounders were repeatedly struck against the granite, gradually fracturing and removing material. Modern research has examined the mechanical properties of granite and dolerite and found that the choice makes physical sense. Dolerite is tough enough to survive repeated impacts, while the granite can fracture under concentrated blows. But quarrying is only the beginning. Breaking a huge block away from the bedrock is one problem. Turning that rough block into a straight, smooth, precisely shaped monument is another. And this is where the argument around Egyptian granite becomes much more interesting. Because when you move from the quarry to the finished object, you start seeing evidence of completely different techniques. The Egyptians were not using one universal tool. They were using a toolbox. And some of those tools were softer than the stone they were working. That sounds impossible until you understand what actually does the cutting. The classic image is simple. An Egyptian craftsman holds a copper saw against a granite block and moves it back and forth until the blade slowly slices through the stone. If that were literally the whole process, the physics would raise an obvious problem. Copper is much softer than granite. So how could a soft metal cut a hard rock? The answer is that the copper did not necessarily have to behave like a modern steel saw blade. Instead, abrasive material could do much of the actual cutting. Think of the copper blade as a carrier. Fine particles placed between the blade and the stone become the cutting agents. As the blade moves, those particles are dragged across the granite. Instead of the copper itself slicing through quartz and feldspar, the abrasive grains gradually wear the stone away. This basic principle is not imaginary. Experimental archaeology has tested ancient Egyptian granite working methods. Researchers have reproduced sawing and drilling techniques using materials available in ancient Egypt, including copper tools and abrasives. The experiments demonstrate that hard stone could be worked using combinations of softer tools and abrasive material, although the process was slow and demanding. That distinction matters. The question is not simply, can copper cut granite? The better question is, can a copper tool, combined with the right abrasive and technique, remove granite? Those are completely different questions. And once you separate them, some of the mystery becomes easier to understand. But another problem remains. The surviving granite work is sometimes extraordinarily precise. There are drilled holes, long cuts, flat surfaces, curved interiors, deep grooves. And some examples have generated arguments for decades because their geometry appears difficult to reconcile with the simplest reconstruction of ancient tools. This is where Graham Hancock and other alternative history writers have focused their attention. Their argument is not necessarily that every Egyptian stone surface requires advanced technology. It is that some examples appear to demand more explanation than the standard cartoon version of ancient craftsmanship provides. And that distinction is crucial, because there is a huge difference between saying, "Ancient Egyptians could not have done this," and saying, "Our simple modern picture of how they did it is incomplete." The second claim is much harder to dismiss. And Aswan gives us another clue. Because some of the strongest evidence does not come from finished monuments at all. It comes from the marks left behind when the workers failed. Ancient Egypt has an unusual advantage for anyone trying to solve this mystery. The workers did not clean up after themselves. At major quarry sites, traces of the process remain embedded in the landscape. At Aswan, archaeologists have documented large numbers of dolerite pounders. One detailed study examined 1,419 examples and found that these tools changed shape as they were used. They began as angular, compact pieces and gradually became rounded through repeated impact. Once they became too worn to work effectively, they were discarded. That is almost like finding the broken drill bits in a modern factory. You can reconstruct the process from the waste. And the tools tell an important story. The Egyptians were willing to use brute force when brute force was efficient. They did not need a razor-sharp instrument to remove granite from a quarry. They could attack the rock again and again, concentrating force in small areas and exploiting the stone's natural tendency to fracture. This is one reason the unfinished obelisk is so valuable. The granite around it records a process rather than merely displaying the final result. Imagine standing beside that enormous unfinished stone. There is no polished monument hiding the evidence. There are trenches. There are abandoned surfaces. There are impact marks. There are discarded stone tools. The quarry itself becomes an archaeological experiment. But there is a subtle lesson here. Ancient technology does not have to look like modern technology. Modern engineers tend to think in terms of specialized machines, hardened cutting edges, powered drills, and controlled feeds. Ancient craftsmen could reach impressive results through completely different combinations of force, abrasion, repetition, geometry, and labor. That does not mean every ancient technique has been reconstructed perfectly. In fact, experiments show that even the accepted dolerite method has limitations. A photogrammetric study of experimental granite quarrying near the unfinished obelisk measured a removal rate of about 216 cubic centimeters per hour under the tested conditions. The researchers concluded that the result argued against using only dolerite pounders for every stage of quarrying and supported the use of different quarrying methods. That finding is revealing. The evidence does not point toward one magical tool. It points toward a combination of methods. And that may be the biggest mistake in the popular version of the story. We keep asking, what tool did they use? The ancient Egyptians may have been asking a different question. What is the most efficient method for this particular piece of stone? For rough extraction, use impact. For shaping, use harder stone and abrasion. For straight cuts, use saws and abrasive material. For holes, use drilling systems. For finishing, use grinding and polishing. The mystery becomes less about one lost machine and more about a sophisticated production system. But then we reach the part that has fueled some of the most persistent claims about ancient Egyptian technology. The drill holes. Some ancient Egyptian drilled holes are remarkably striking. Their interiors can contain grooves and marks that appear to spiral along the wall. To modern eyes, that immediately resembles the signature of a rotating tool. And that creates a fascinating problem. How could Bronze Age craftsmen rotate a hollow drill through granite while maintaining a controlled motion? Alternative history researchers have pointed to these marks as evidence that the conventional explanation may be inadequate. Engineer Christopher Dunn, for example, has argued that certain ancient drilling evidence displays characteristics he believes are difficult to reproduce with the commonly proposed methods. The most dramatic claims concern the apparent feed rate of ancient drilling. Some interpretations have suggested that ancient tools advanced through granite at rates far beyond what should be expected from primitive abrasive drilling. But this is where the evidence needs to be handled carefully. A striking groove is not automatically a measurement of drilling speed. And an unusual mark is not automatically evidence of lost high technology. The ancient Egyptians may have used rotating drills with abrasive material, and experimental archaeology has demonstrated that such techniques can work. At the same time, reproducing every ancient example exactly is a much harder challenge. That distinction is essential. Because a failed modern experiment does not prove an ancient machine existed. But a successful experiment does not necessarily prove that every ancient example was produced in exactly that way. Archaeology often lives in that space between the two. And there is another complication. Granite is not one uniform material. It contains different minerals with different physical properties. A cutting process interacts with quartz, feldspar, mica, and other components in different ways. The behavior of the tool can also change depending on pressure, abrasive size, water, rotation speed, and the geometry of the cutting edge. That means an ancient groove can contain a record of many variables at once. This is why the debate has survived. One side can point to experimental replication and archaeological tools. The other can point to unusual surfaces, geometry, and measurements that appear to deserve more investigation. Neither side needs to pretend the other has disappeared. In fact, the most interesting conclusion may be that the ancient Egyptians understood something modern viewers often overlook. They did not have to make their tools harder than granite. They needed to make the entire cutting system work. The tool, the abrasive, the pressure, the movement, the water, the operator, the time. Together, those became the technology. And once you see technology that way, an apparently impossible feat starts looking very different. There is one word that can completely change the granite cutting debate: abrasive. Modern people are accustomed to thinking of cutting edges as the important part of a tool. A knife has a sharp edge. A saw has teeth. A drill has a hardened bit. But abrasive cutting works differently. Instead of relying on one hard edge, countless tiny particles do the work. The ancient Egyptians had access to abrasive materials, including quartz-rich sand and other hard mineral particles. When those particles are trapped between a tool and a stone's surface, movement can turn them into microscopic cutting points. The metal tool provides pressure and movement. The abrasive provides the hardness. The stone provides the material being removed. That simple combination can accomplish far more than the appearance of a copper blade suggests. This also helps explain why ancient saws did not need to resemble modern saws. A copper blade could act more like a flexible carrier for abrasive slurry than a modern steel saw. The same principle can apply to drilling. A hollow tube does not necessarily need to be harder than granite if abrasive particles are constantly brought into contact with the stone beneath pressure and rotation. The process is slow. It is labor-intensive. It requires skill. But slow does not mean impossible. And ancient Egypt had something modern experiments do not have: an unlimited supply. Time and organized labor. A large state could dedicate specialists to a project for years. Workers could repeat the same operation thousands of times. A technique that looks inefficient when performed for an hour in a laboratory may look very different when thousands of skilled workers and craftsmen operate within a large construction system. Still, that does not solve every question. There are surfaces that remain difficult to reproduce. There are measurements that continue to be debated. There are ancient marks whose exact production sequence is uncertain. And there is an important difference between demonstrating that a method is physically possible and proving that the ancient Egyptians actually used that exact method in a particular monument. That is where the Graham-Hancock argument becomes most useful as a challenge. Not because every alternative explanation automatically wins, but because it forces attention onto the evidence itself. If an accepted method can reproduce an ancient feature, show it. If it cannot, test another method. If several methods could have produced the result, compare them. That is how the question should be approached. The real enemy is not skepticism. It is assumption. And the granite itself does not care which side of the argument wins. It simply preserves the marks. The deeper story may be less about a lost supermachine and more about lost practical knowledge. A modern engineer can look at an ancient Egyptian saw and see copper. An ancient craftsman may have seen an entire system. He knew how much abrasive to add. He knew how hard to press. He knew when the tool needed adjustment. He knew what the stone felt like under the blade. He knew when a surface was beginning to bind. He knew how to keep a cut straight. That knowledge is difficult to recover archaeologically because expertise leaves fewer physical remains than tools do. A hammer survives. A technique does not. A copper blade can corrode or be recycled. A craftsman's experience disappears when the craftsman dies. This is one reason ancient technology can look mysterious. We often have the object but not the instructions. The Egyptians also seem to have understood the properties of different stones exceptionally well. They selected materials for specific purposes. They transported massive blocks over long distances. They shaped hard stones with repeated processes. They polished surfaces until they reflected light. None of this requires us to imagine that they possessed machines identical to ours. It requires us to recognize that technological sophistication can exist without modern industrial equipment. The evidence from Aswan makes that especially clear. Dolerite pounders were not random rocks. They were selected, used, reshaped through wear, and discarded when their performance declined. Archaeological research has even examined their sources, forms, and patterns of use. That is a technological tradition. And the recent quantitative work on dolerite and granite adds another layer. By comparing the mechanical properties of the two rocks, researchers found that the ancient choice of dolerite makes sense from the perspective of fracture mechanics. So perhaps the most important correction is not that everything Egyptologists have said about granite is wrong. It is that the popular version is too simple. Ancient Egyptians used copper tools is incomplete. Ancient Egyptians used only stone hammers is incomplete. Ancient Egyptians had an unknown advanced machine is also an enormous leap beyond the evidence. The reality may have been much richer. Different tools for different jobs. Different abrasives for different stages. Impact for extraction. Sawing for separation. Drilling for holes. Grinding for shaping. Polishing for the final surface. And generations of craftsmen learning how to combine them. That is not primitive. It is engineering. Now we can return to the title. Were we wrong about how the Egyptians cut granite? If the claim means that the ancient Egyptians did not simply take soft copper blades and slice through solid granite like modern saws, then yes, the popular picture is misleading. But if the claim means that archaeology has no plausible explanation for Egyptian granite working, the evidence does not support that conclusion. There are real tools. There are real quarries. There are real experimental studies. There are real traces of impact, sawing, drilling, grinding, and polishing. The physical evidence shows that ancient Egyptians had effective ways to work hard stone. At the same time, some individual examples remain difficult to reconstruct with complete confidence. That is where the mystery remains alive. The most honest conclusion is not that a hidden machine has been proven. It is that the ancient Egyptian stoneworker deserves more credit than the phrase, copper tools, gives him. Because the copper was only one part of the system. The abrasive mattered. The pressure mattered. The motion mattered. The shape of the tool mattered. The experience of the craftsman mattered. And the enormous organization behind the project mattered. A modern person may see an enormous granite sarcophagus and wonder what machine could have made it. An ancient craftsman may have seen something completely different. A sequence. First remove this material. Then straighten this surface. Then drill here. Then grind this edge. Then polish the final face. Thousands of small decisions can produce something that looks impossible when viewed only as a finished object. And that may be the most important lesson hidden inside the granite. Ancient technology does not have to resemble modern technology to be sophisticated. The Egyptians may not have needed a machine capable of overpowering granite. They may simply have understood how to make granite surrender one tiny fragment at a time. The unfinished granite at Aswan may be more revealing than the polished monuments of Egypt. It shows the process in mid-sentence, the trenches, the abandoned stone, the impact marks, and the worn tools that tell us ancient workers attacked granite with patience and method. Modern research supports the physical logic of dolerite pounders, while experimental work shows that abrasive techniques could be used for sawing and drilling hard stone. But the most fascinating questions remain in the details: how individual tools were combined, how craftsmen controlled difficult cuts, and how much practical knowledge has disappeared with the people who mastered it. So perhaps the real mystery is not whether the Egyptians possessed impossible technology. It is how much technology can vanish when the tools survive but the knowledge behind them does not. Which part of Egyptian granite working do you think still deserves the most investigation? Subscribe for more investigations into the technologies, discoveries, and mysteries hidden inside the ancient world.